Lesson 2, another look at particle motion. In this lesson, we're going to put together all the big ideas for modeling motion problems and how they're going to present themselves on the AP exam. So this is kind of the last time we look at particle motion. Excuse me. One important thing we want to recognize is that motion meant a particle moved in a straight line, but it was moving on an axis, not along the graph of the function. And now we're going to see it's possible for us to work in both directions. Here's an example. If an object is traveling in a straight line, then its velocity can be expressed as the integral of acceleration. Let's take a look. We know the net change theorem tells us that the definite integral of the rate of change of a quantity f prime of x will give us the total change, or that net change in that quantity on the interval. Now, we've got to think about that idea, net change. We're given an object's velocity, and the question stem is asking about the object's position. We have to understand which definite integral is necessary to answer the prompt correctly. If they're asking for displacement, we consider that positive area and subtract the negative area and add back the positive area in this example. If we're considering total distance, we want the absolute value of velocity, so we're adding area above the axis and below the axis to get the total distance traveled. And if we want the actual position, then we need to know that initial condition, where we add that initial condition to the accumulated area. So let's say we're given that initial amount, S sub 0 is 4. We want to find the displacement, or the total distance traveled, and the position on the interval from 0 to 10, where velocity is in meters per second. Here's our velocity graph. So in this instance, if we calculate the accumulated area from 0 to 10, that's going to be 18 minus 12, which will be displacement of 6. If we calculate the absolute value of velocity, which is the total distance traveled, that's 18 plus 12, or a total distance of 30 meters. This is 6 meters. And then if we want to know the actual position, that would be the initial condition. We started off at 4 initially and accumulated that area from 0 to 10. So the position is 4 plus 6, or 10 meters from its starting point. So just be careful which rule that you're using. Here, the graph at the right represents the velocity of a particle that's moving along the x-axis on the closed interval from 0 to 8. And velocity is measured in units per second. So for part A, what interval of time or intervals of time is the particle moving to the right, and how do you know justify your answer? So many times on the AP exam, we have to justify what we know using the proper language. In this case, I'm going to start off by saying wherever our velocity is positive, where velocity is positive, the particle would be moving to the right. Where velocity is positive, particle moves right. So where does that occur? Where the velocity is positive, from 0 to 3 and from 7 to 8. So this would be on 0 to 3 and 7 to 8 seconds, our units. Then on part B, on what interval or intervals is the particle slowing down? Justify your answer. How do you know? Well, the particle is going to slow down where velocity and acceleration have different signs. Where would that be? Where velocity and acceleration have different signs. Where the graph is decreasing and above the x-axis, or increasing and below the x-axis. Where the graph is decreasing and above the x-axis, where would that occur? 2 to 3, 2 to 3, the graph is decreasing and it's above the x-axis, or where it's increasing and below the x-axis. So that would be on 6 to 7, or increasing and I said below and I started to write above. Increasing and below the x-axis. So that would be on 6 to 7 seconds. Part C, when is the particle stopped and changing directions? Justify your answer. So the particle would be stopped where the velocity is 0, where velocity is 0. That's the x-intercepts. You may have to go back and look at our graph here. Let's go back and look. So the x-intercept, so at 3 and at 7, because this is a derivative graph, velocity is 0, at time equals 3 seconds, and at time equals 7 seconds. Stopped and changing directions. You see how you know it's changing directions? We're going from positive velocity to negative velocity, and then negative velocity to positive velocity. Okay. Now part D, on what time interval is the acceleration 0? Justify your answer. Acceleration would be 0 where velocity is constant. And there are 2 places where velocity is constant, right here from 1 to 2, and right here from 4 to 6. So what time is it where acceleration is 0, velocity is constant? So when you're thinking about the graph, you're really looking at where the graph of the velocity curve has horizontal tangent lines. That would be another way to say that. So between 1 and 2, and then again between 4 and 6 seconds. Okay, here's another table problem. College Board likes table problems. A city bus accelerates as it leaves one stop, then it decelerates as it comes to another stop. The chart below measures the velocity given in miles per hour between each stop. We want to find the distance in miles the bus travels between every interval or stop using the trapezoidal rule. So the trapezoidal rule is half of the height, which is the width of our interval, the change in the time, and then the velocity, or the bases, the sum of the bases. So from geometry, we know that. How that relates, I don't know, let's say if we go over here and look from 20 to 25, that time interval from 20 to 25, from time equals 20 to time equals 25, that height is 5, but it's in what, minutes? That's in minutes, and where our velocity is miles per hour. So we've got a little, let's make sure I'm doing this right. Yes, time is in minutes, velocities in miles per hour. So this is 5/60 of an hour. And the heights are 32 and 4. So we want to add together 32 and 4. That would be 36. And 5 divided by 5 times 36 divided by 120 turns out to be 1.5 miles. So at 4, that would be 1.5 miles from 20 to 25. So that's the procedure you would follow for each one of those. You might want to stop the video and calculate each of those values, and then we'll finish the questions. Okay, you've had enough time to do that. These are the values I got. You want to check that you have the same amounts that I have, that I haven't made any mistakes. And then to find the total distance the bus traveled in that 60-minute interval, we would want to add up each one of those areas to get the total distance. The area would be the total distance traveled. And I get roughly 17.2486 miles. Hopefully we're in agreement on that. Now let's see, some motion problems require us to find the actual position. So remember, we're going to use initial conditions as we saw in an earlier lesson. The actual position. Remember, the definite integral only tells us the change in position, and we want to accumulate, so we want the initial condition. So example 3, an object moves in a straight line with this velocity in meters per second, where time is given in seconds. And at 5, the object's distance from the starting point is 12 meters in the positive direction. So there's our initial. We want to write an integral expression that will compute the object's position at 10 seconds. So we want initial plus displacement. Initial plus displacement. Can you do that on your own? Initial plus displacement. Whoop. Can't get that to move. Here we go. So initial is 12, and displacement goes from 5 to 10. Here's our 10. From 5 to 10 of radical 3t minus 2 dt. Now next, for the next one, use a graphing calculator to find the actual position of the object at 10 seconds. So we're actually going to jump over to our calculator and let that estimate be done for us on the calculator. So we can go over here, and in our graph window, we're going to put the square root of 3x minus 2, and then enter 12 plus menu for the integral from 5 to 10 of the velocity curve that we have in the F1. Whoop. of our velocity function, which is in the F1 window. Whoa, that doesn't look very friendly, does it? There you go. I needed to put a decimal in the Inspire right here on the 12 so it would calculate for us and not give exact numbers. We have 34.5089. So going back to our screen, we've got roughly 34.508 or 508 or 509 meters. It's the actual position of the object at 10 seconds. So it was going to the right, still going to the right. A particle is moving along the x-axis with this velocity. It's measured in meters per second after t seconds, and our initial is s of 0 is -3. We want the displacement of the particle on the time interval from 1 to 7 seconds. So from 1 to 7 seconds, the velocity is -1/3 t cubed plus 7/2 t squared minus 10t from 1 to 7, which becomes 343 over 3 negative plus 343 over 2 minus 70, and then -1/3 plus 7/2 minus 10. Need a little more room here. This is -114 plus 168 minus 60. So I'm adding these together, and these together, which becomes -6 feet. So the displacement was 6 feet to the left. And then what's the total distance traveled by the particle on the time interval? So that would be absolute value. We want the from 1. And we've got to consider where that graph becomes negative. I'm thinking about, let's go graph that real quick. So it's negative x squared plus 7x minus 10. Now on the AP exam, you wouldn't have a calculator, you'd have to calculate it, but I just want you to see graphically without factoring that at 2 and at 5, the graph goes from negative to positive to negative, and we want to calculate from 1 to 7, so we need to consider from 1 to 2, 2 to 5, and 5 to 7. So our integral needs to reflect that. From 1 to 2, absolute value, plus the integral from 2 to 5 for the velocity, plus the area from 5 to 7 for the velocity. And that would give us, let's see, I've already pre-done this, so this one turned out to be -22 over 12. The middle one turned out to be 4.5, and the last one turned out to be 26/3. So getting a common denominator of 12, we have 22 plus 54 plus 104 over 12, and that area adds up to 15 feet. So it's important to pay attention to where the graph becomes negative. Suppose you're driving in traffic behind a large bus at 66 feet per second. This is 45 miles an hour roughly. When you finally get a chance to pass, you step on the accelerator, giving the car an acceleration of 4 over the square root of t, where acceleration is measured in feet per second and time is measured, we're missing a time is measured in seconds. How fast are you going 16 seconds later when you have passed the bus? So velocity is the integral of acceleration, which means velocity is, looking at this, 8 square roots of t plus a constant. And what was our constant? It says initially we were moving 66 feet per second. So our c value is 66. This is our c value. And the velocity at 16, after we've gone 16 seconds, is 8 times the square root of 16. So 32 and 66 is that 98 feet per second. So we're moving at 98 feet per second at that time. How far did you travel during that time? Well, that would be the absolute value, okay, of velocity. So during that time, those 16 seconds, we want the absolute value of velocity. And that would be, let's see, t to the 1/2. So 16 over 3, t to the 3/2 plus 66t from 0 to 16. And substituting 16, cheating a little bit here with my calculator, 1024 over 3 and 1056 is roughly 1397.3 repeating. And our units are feet. So that's how far we've traveled during that 16 seconds. And you want average velocity. So average velocity is displacement over time. Displacement divided by time. Oh, sometimes my pencil just gets a mind of its own. So displacement over the 16 seconds, that's a 9, is about 87.33 feet per second for the velocity average velocity. Okay, 2 more to go. How about you drop your calculus book from a window 48 feet above the ground? How long will it take your book to reach the ground? On planet Earth. So velocity is 0 because you're holding it and then you drop it. And one thing you may or may not know is on planet Earth, when the units are feet, the gravitational constant is negative 32 feet per second, holding us here on the Earth, keeping us from floating away. So the position at 0 is 48. And if we integrate velocity, if we integrate acceleration, we'll get velocity. And that first constant is going to be 0. This is our c sub 1. We'll call that c sub 1. And then if we want position, to get position, we would have to integrate velocity. Plus c sub 2. So this is our c sub 2. There's our position function. And now we can answer the question, how long will it take your book to reach the ground? So the question is basically this: when is s of t going to be 0? That's what we need to answer. And that would be 48 over 16, the square root. So when is 16 t squared equal to 48? When t is plus or minus square root of 3. But in the real world, we don't have negative time. So square root of 3 seconds it takes, or about what, 1.7 to reach the ground seconds. Part B, what's the velocity of the book at the instant it reaches the ground? Well, we know what velocity is because we just calculated it. Velocity was negative 32 t, and the velocity at the square root of 3 is going to be negative 32 times the square root of 3 feet per second if you wanted the exact answer. If you wanted a decimal approximation, take your calculator out and find that it's about 55 feet per second at impact. Okay, and then you could calculate miles per hour if you wanted, about 40 miles an hour. All right, last example. A particle moves along the x-axis so that its velocity at time t for the first 15 seconds is given by a differentiable function whose graph is shown here. And you can see we've got the areas all along that curve, stopping at 15. Horizontal tangent lines are at 6 and 11. So 6 and 11. Areas of the region are bounded from 0 to 3, 3 to 9, 9 to 13. So this is pretty much an example of a free response kind of a question. Let's see if we can keep 2 windows open at a time. And then for part A, on 0 to 15, find the time and the position of the particle when the particle is farthest to the right and justify how we know. So first we could just look at the first interval from 0 to 3. Find out what the x of 3 is. It would be the initial value. Initially we're at 4, so the initial condition is the x of 0 is 4. So we're starting at 4, and we're going to accumulate the area from 0 to 3 on that velocity curve. And that area is 6, so from 4 to 6, we've got 10. Did they give us units? I don't think they did. Okay, and then at 13, 13 is the other 0. We have initially 4 plus 0 to 13. So we're adding 4 plus 6 minus 9 plus 3. We end up with 4 because those are 9 and that's 9. Okay. So the particle's at 4. So based on those calculations, what do we know? That the velocity is positive on 0 to 3, and again on 9 to 13. That means our particle is farthest to the right at 3. I'm out of space here. At t equals 3. Okay, so the particle is farthest to the right when it's at 3 units of time. Now part B, for how many values of time on that interval from 0 to 15 is the particle at 4? Explain our reasoning. Well, we know that the particle is continuous. Let's see, let me erase some of this. So there's going to be, is it 3 values? Let's put some words to this. So the particle is continuous, because I'm thinking intermediate value theorem here. On 4 to 10, 4 to 3, the particle is continuous on x equals 0. It's also continuous from 3 to 9, and from 9 to 13. Could have done this with a table, I think. Let me stop. Okay, I regrouped. I think I would rather do it with the table over here. So let me get rid of some of this. So first of all, we know to use the intermediate value theorem, we have to have continuity. So first we want to say that the particle is continuous on each one of those intervals. And if I look over here at this table, all I did was accumulate the area for each little segment based on the fact that we're at 4 initially. So when x is 0, y is 4. Then when x is 3, y is 10. Moving on over to the next 0, when x is 9, we've got 4 plus 6 minus 9, we're at 1. And when we get to 13, we're adding back 3 to that 1 and have 4. When we get to 15, we're subtracting 2 and we have 2. So the prompt is asking us on those 15, on that interval of 0 to 15 units of time, is the particle at 4, and how do we know? So by the intermediate value theorem, we could say that there's going to be 3 times, 1, 2, 3, where t takes on the value of 4, and put that into words. Particle is continuous, so by the intermediate value theorem, there are 3 values, because remember we're looking intermediate value theorem as the y value, 3 values for time where the particle is at 4. For how many values? So 3 of them. One set initially, again at 13. Wait, did I mess up my chart? 0, 3, 9, 13, and 15. Hold on here, I made a mistake. Wrote my table wrong. Okay, got that fixed. It's still going to be 3. Let me explain. So intermediate value theorem, we're going to take on every value. It's got to pass through 4 here, coming back down. So 1 time here, 1 time in between 3 and 9, another time right here. So 3 times that the particle will be at 4. Sorry for the confusion. All right, so go on to the next table. On what interval is the speed of the particle increasing? Can you give a reason for that? Oh, I don't have my graph. Okay, so the speed of the particle is going to be increasing where the velocity is increasing. So let's go back and take a look at the picture. That would happen on 9 to 11, because they told us that there was a horizontal tangent line at 11. So right in here, velocity is increasing. And where velocity is negative and decreasing, that would be from 3 to 6, because 6 was the other horizontal tangent line. So from 3 to 6, and over here from 13 to 15. So we know the speed's going to slow down when the signs are different. It's going to speed up when the signs are the same. What interval is the speed increasing? Increases on intervals 9 to 11, because velocity is positive and increasing. The speed is increasing. And then on 3 to 6 and 13 to 15, because velocity is negative and decreasing. Now, I'm talking about the velocity graph because I was given the velocity graph. You notice I didn't say anything about acceleration. I know acceleration is positive when the velocity graph is increasing, and acceleration is negative when the velocity graph is decreasing. But they gave us a velocity graph, so we're going to speak to the velocity graph. During what time intervals, this is the last one, if any, is the acceleration of the particle positive? So once again, let's go back and look at the graph. Where's acceleration positive? Where velocity is increasing. So where's velocity increasing? That's happening on 6 to between both horizontal tangent lines. So from 6 to 11, velocity is increasing. So acceleration is positive on the interval 6 to 11, since velocity is increasing here. Ooh, this was a long lesson. Now, on the AP exam, if this was a free response question, you wouldn't want to write out full sentences like that. I'm doing that just for understanding. But on the AP exam, you might write acceleration is positive on 6 to 11 since velocity I don't want to write that, since velocity increases. Oh, won't erase. velocity increases here. Okay, long lesson. Lots of practice for us on the homework.